Hey there everybody, and welcome to a brief video on section 3.7 in lieu of having class. So this section is pretty short because there's nothing really new in it, especially because we went out of order and covered section 3.9. So the point of this section is just to reinforce what we've talked about many times, that a derivative is a rate of change, something which occurs in all sorts of fields like physics, economics, and so on. So under the hood, something in chemistry can be the same thing as something in economics if it's a rate of change. So the calculus, the mathematics, can tie together all these disparate topics. So that's what this section talks about. So just for example, in chemistry, a chemical reaction results in the formation of one or more substances, and you often use equations like this to denote such a thing. So A plus B combined to give you C, and you can use notation like this to denote concentration. And so you can talk about the rate of change of the reaction. So how quickly is C being made? Slowly or quickly? So D concentration C dt is the rate of change of that concentration of the product that's being made. Also in chemistry, there's something called compressibility. So if a given substance is kept at a constant temperature, volume then depends on its pressure. And the isothermal compressibility, a fancy term, impress your friends, is defined to be this. Like this is a definition here. 1 over the volume with a negative, and then the rate of change of volume with respect to pressure. So this dVdP is measuring if pressure changes, how does volume change? Yeah, so this measures how fast per unit volume the volume of a substance decreases as the pressure on it increases, while we again keep temperature constant. So here are two concepts from chemistry, the rate of change of a chemical reaction, isothermal compressibility, that are just derivatives. I mean, this one here has a scale factor on it, but it's just really, you just care about this derivative right here. dVdP, over here, dCdt. So two sort of seemingly different physical reactions or whatever, physical processes that under the hood are just the same thing. So mathematically, dCdt, dVdP are the same thing. So here's an example that we would have done in class. And since we've done section 3.9 already, this one goes a little more quickly, so I've filled in the details here, but just to explain what's happening, we're thinking about when air expands without gaining or losing heat. It turns out that the pressure times volume raised to the 1.4 power is a constant. So this is a chemistry equation that the chemist figured out. So I should emphasize that when you do homework in this section, it is of course understood that you don't know any chemistry necessarily. But you don't need to know any chemistry to answer this question. You're handed an equation here. Pressure times volume to the 1.4 is C. Now C is a constant, but this air is expanding. So over time, pressure is changing and volume are both changing over time. So notice this is a related rates question. So it gives you a bunch of information and then asks, how quickly is the volume increasing at this particular moment in time when all these numbers hold? So volume is 400 and pressure is 80. And so we've already done problems like this in class. So if we'd done things in order, we would have spent a ton of time on this. But since we've already started section 3.9, let me just say, this is a related rates problem where they've handed you an equation. You don't have to come up with your own equation. So let's differentiate it with respect to time. C is a constant, and the derivative of a constant is 0. This is a product right here. P times volume to the 1.4. So the product rule says, leave the first thing alone, multiply by the derivative of the second, and we have something to a numeric power. So stuff to a numeric power, bring the power down, decrease the power by 1, times the derivative of the inside, which is volume, and then add the derivative of the first term. So the derivative of pressure times the second term left alone. So you get an equation like this from the calculus, and then you can go through and plug in all the values. So pressure, the problem says, is 80 kilopascals. It's worth noting here, it says the pressure is decreasing at a rate of 10. That's why there's a negative here, negative 10, not positive 10. You plug all these numbers in, you isolate V prime, and you get 35.7 cubic centimeters per minute is the rate of change of volume. So here's a chemistry example where you can use a derivative to figure out how volume is changing, the volume of this air as it expands adiabatically, another fancy term. It says round your answer to the nearest whole number. I should have read the question better. So I guess 36 is what this wants. Anyway, 35.7 or 36. So in physics, the classic derivative you would see in like general physics 1 would be just thinking about velocity and acceleration. The farther you go in physics, the more different derivatives you see, by the way. But so this is sort of a baseline here. But if you have a measurement of height or distance or something, the derivative, written as s prime of t or ds dt, is the velocity. If you take the absolute value of that, that's the speed. So the absolute value just means ignore any negatives. The second derivative is the acceleration. Negative velocity means leftward movement or downward movement, depending on your orientation. So the derivative is telling you the direction of movement. So again, this is just like a classic physics thing. Velocity, speed, acceleration. Those are all examples of derivatives. If you have a metal rod lying on the x-axis, you can let m of x denote the mass at position x. So imagine a rod that starts at the origin and stretches over to x equals 4 or something. Then m of 1 would be the mass at position 1, m of 2 the mass at position 2, and so on. So mass is a function of position on the metal rod, and then dm dx, the rate of change of mass with respect to position, has a name, an official name, linear density, and the units are kilograms per meter in physics. So this m prime, this is like velocity on some level. I mean, the word velocity makes no sense here, but you're measuring how mass changes with respect to position. So instead of meters per second, it's kilograms per meter, but it's the same idea. If you have charge in a wire at time t, so charge depends on time, then dq dt is the current measured in coulombs per second, usually called amps. Current is measured in amps. And I mean, like I said, physics is just full of derivatives, especially the higher you go in it. So like heat flow, I mean, there are entire courses on like partial differential equations in physics that you can take beyond the scope of this course. But again, there's like under the hood, current, linear density, velocity, mathematically, those are all the same thing. They are also equivalent to, the rate of change of a chemical reaction mathematically. It's all the same. Biology, oftentimes you're interested in the rate of change of populations. So that's what this is. Number of individuals or grams of bacteria or whatever per time. So this, you could be watching bacteria grow. You could be watching the population of wolves change. You could be measuring the rate of change of infected people during a pandemic, something recently relevant. And so it turns out, by the way, that a lot of models, a lot of the COVID models just ran on using derivatives because we could sort of measure the rate at which people were getting infected, and we could use that to build models to make predictions. In economics, you have a cost function, revenue function, profit function. So C of X is the total cost you incur by producing X units. Similarly, R of X, P of X, total revenue, total profit at producing X units. Marginal cost is a technical term. It's just a derivative. The rate of change of cost with respect to units produced, and so on for the other two. So C prime of 100, for example, if you want to think about what that is, you have to ask yourself, if I've already made 100 units, what is the approximate cost of making the next unit? That's what C prime of 100 represents. So economists throw this word marginal in front of words all the time to mean derivatives. So marginal demand, they have some demand function going, which we're not going to talk about right this second, but marginal demand just means the derivative of that, the rate of change of demand. So marginal cost, marginal profit is mathematically the same thing as rate of change of bacteria population, the same thing mathematically as current in a wire, and so on. So the math unifies all of these. That's part of the power of mathematics. So there's many other things I could list here. So at some point there's diminishing returns, but you could think about the spread of ideas. So like, are ideas increasing in popularity or not? There's sort of a rate of change there. Psychology, people have studied the rates of learning things, In geology, there's a rate at which an intruded body of molten rock cools by conduction of heat in the surrounding rocks. So geologists have a technical term for that I didn't bother to look up, and so on. There's just so many things where you might want to measure how something is changing, a rate of change, and a derivative can do that for you. And that sort of unifies all of these topics. So the big idea here is that mathematics, like, why is math so powerful? And its abstractness. So when you think about a derivative, you don't have to be thinking about any particular physical thing at all. You've sort of removed all physical meaning when you write down f prime of x. But then when you start putting physical meaning back on, a lot of different physical phenomena can be modeled by the same kind of mathematical idea. So that's the power of mathematics. A single mathematical idea can have many different interpretations and many different fields. So again, none of us are economists, none of us are biologists, etc. But we can still do something with biology as long as we just know, like, if we knew what this function was, like if we knew f of t was whatever, we could think about population rate of change. So we could do the math on this topic. So again, here, I don't really know where this equation came from. I'm not a chemist, but I can answer a question like this because I know the math of derivatives. So that's really, really nice. So finally, this sheet comes with exercises. The solutions are already there, but I wanted to quickly talk through some of them and fill in some of the work that we would put on the board. So this exercise 1, the point of it is just to help you keep track of what things mean. So S is position, T is time. So S of T tells you where you are at a particular time. So if you're asked, where is the particle at this time? You find S of 2. What is the velocity at this time? Now you got to take the derivative and plug in 2, S prime of 2. Notice that with this one, I'm not setting S prime equal to 2. If I asked you, when is the velocity 2 meters per second? You would take the velocity function here and set it equal to 2. But I'm saying, no, here's just the time I care about. So you plug in that time. Same thing with acceleration. There's the acceleration function. So there's the acceleration at time 2. The speed of the particle is just the absolute value of velocity. So once you have this number, you can just make it positive, and that's the speed. Okay, when is the particle not moving? Not moving means the velocity is 0. So in English, velocity is 0. So you set that equal to 0, you can factor out a time, you get those 2 times. So initially, the particle is motionless, and then a third of a second later, the particle is motionless. And then when does it have 0 acceleration? Take the acceleration function, set it equal to 0, you get time 1/6. Okay, one more here. Again, the answers are at the bottom, but I wanted to fill in some of the work. So sodium chlorate crystals. So when I read this, I'm already scared because I don't know any chemistry. But then it says, if V is the volume of a cube with side length x, let's calculate the derivative of V with respect to x. And then I think, oh, thank God, I don't have to know any chemistry. I'm just dealing with a cube. That cube happens to be a sodium chlorate crystal, but who cares? The math doesn't care that it's a sodium chlorate crystal. The math sees cube. I know the volume of a cube, so V of x is x cubed. The volume is x cubed, so I can measure the rate of change of that. So V prime is 3x squared, and you can plug in a 4. When x equals 4, and get 48. And notice the units here are kind of wacky. So volume is measured in cubic millimeters in this question, and x is measured in millimeters. So V prime, the units of that are dependent units per independent units. So volume is dependent, they are volumes units, and x is the independent variable, and they are its units. So it looks kind of funny to write cubic millimeters per millimeter. You might want to cancel that and just write millimeters squared, but you don't want to do that. This is not like a literal fraction. So if you wanted to interpret this number, you would say, well, if we increase, not we, we're not speaking French, just one we, sorry. If we increase the side length of the cube from 4 to 5, so if we're at 4 in side length, what if we increased up to 5? The volume would increase by about 48 cubic millimeters, or you could say this. When the side length is 4 millimeters, the volume is growing at this rate, 48 cubic millimeters per millimeter. Okay, so this section again is kind of just a jumble of like, hey, you know what a derivative is? Guess what? Like, you can do some chemistry a little bit, you can do a little bit of physics or whatever. You just have to keep track of what the derivative is measuring. Uh, and there's kind of a mixture in this section a little bit. Mostly it's like this. Notice there's no implicit differentiation here. There is no implicit differentiation here. So most of the section there's no implicit differentiation going on because 3.7 comes before 3.9. But you might see something like this, kind of anticipating the related rates problems that we did uh, in class on Wednesday. So if you want to, you can do the rest of the exercises. There's just solutions here without work filled in, but you can try 3 and 4, and I guess 5 and 6 also have just solutions. So you can see what you think about those, and if you have questions, you can ask on Monday. But that's section 3.7.